As we start investigating the ways that a program can be optimized as it's compiled, some of those optimizations will be specific to the target machine. Today, however, we'll mostly look at optimizations that are generally useful independent of the machine. Machines have enough in common that there are things that almost always make things run faster, like not doing any work at all as opposed to doing some work every time in a loop. These optimizations are the kinds of things that compilers can often do for us, and they're the kinds of things that we might do by hand, either because the compiler can't see through some functions or some other information, or because we want to make sure that they happen. And the three that we'll look at today are generally called code motion, as moving expressions from one place to another where they're executed less frequently. Strength reduction, that's going to mean using simpler operations in place of more complicated operations because we know something about the simpler use, like it's a power of 2. And sharing common results. This is something like code motion, but it's pulling a similar expression from many places and moving it into one place. That's often called common subexpression elimination because you're eliminating the copies of the subexpression. So let's look at some examples of these things, starting with code motion. Here we've got a set row function. The key thing is there's a for loop, and we're installing into an array A based on the values in an array B, and we have to compute a place in A for that value to go to. Now you'll notice that the loop variable is j, so that means n times I is never going to change as this loop goes through. And it would be better to lift that n times I out and do it just once. So this is something you might do by hand, or it's something that an optimizing compiler will be able to do in this case. So that means we've taken the n times I multiplication out of the for loop, doing it just once at the beginning, and then use it every time in the loop. So this is going to be faster because doing something one time is going to be faster than doing it n times, as long as n is at least 1. And I say the compiler can do this if you look at the GCC-01 output. So just basic optimizations enabled. This is a basic optimization. You'll find that there's just one multiplication, and then here's the loop, L3. We have the comparison and jump, and you don't see any multiplications inside of there. In fact, the compiler has noticed something else is constant. There's another bit of arithmetic, which is taking this multiplication and adding it to the base address A, in addition to adding j. So this number added to A is always going to be the same through the loop, and the compiler has done that, just has moved that computation out to the top, computing a row pointer that it uses every time through the loop. In other words, it changes the C program to something like this: compute n times I once, then use n times I once to get row P, and then just increment row P as we go through. Another optimization that a programmer or a compiler might implement is strength reduction. And we've talked about this one. We've talked about, instead of using a multiplication instruction, just using a shift instruction, for example, because you know the number 16 is a power of 2, and so it can be done with a shift. And if we were multiplying by 17, then the question becomes less clear. Is it cheaper to do one multiplication, or is it cheaper to do a shift and an add? It's probably a shift and an add, but it depends on the machine to some degree. But when we know that one operation can be replaced by a simpler operation, it's practically always a win. And again, this is the kind of thing a compiler does. In that case, 16 times x. If you put that in a program and compile it with -01, then you'll get a shift instruction instead of a multiplication instruction. But strength reduction can show up in less obvious places too. Here we have a multiplication. This multiplication is inside a loop. This time it needs to stay in the loop because it's n times I, and I is the loop variable for this outer loop. We've already lifted it out of the inner loop. So even though this multiplication in principle needs to happen every time, in fact, this multiplication corresponds to a sequence of additions. Because we're multiplying by I, because I is growing by 1, we could change that by incrementing n plus ni by n every time around the loop. And if addition is cheaper than multiplication, then this will be a win overall. Even though we're sort of using up an extra register as we go around the loop, that extra register is likely to be available anyway. So again, if you compile this code, with -02 in this case, then we'll see that the compiler does this transformation for us. It ends up with a pointer to A. In fact, it has that same kind of merging that we saw before, where the pointer to A is incremented by 4 times n, since A has integers here. Just as you would hope and expect. And finally, we have common subexpression elimination, where suppose that we have this array val, and we're pulling a few entries close by in that array. So we have I times n plus j, and we're getting the first couple before that and the first couple after that, and adding them all together. And you see, as written, then we have many multiplications of I times n plus j, written 4 times, so a natural thing to do would be to only compute that once and to use that result. This is the kind of thing a programmer might do by hand just to make the code clearer, to make it more obvious that it's the same computation being used every time. It's also this kind of thing that a compiler might do. Here's a slightly less obvious case. So you don't see 4 copies of I times n. You see an I times n a couple of times. And you see a lot of plus j's, but the plus j's are being added to different things. But in this case, you can rearrange the computation and get more commonality. So we can again compute that same I times n plus j, but then after we do that, subtract off an n to take care of the -1 here, add on an n to take care of the plus n there, and keep the -1 and +1s here. So this is a slightly fancier form of common subexpression elimination, but it is definitely worthwhile because it's replacing 3 multiplications if you just straightforwardly compile the code on the left with a single multiplication on the right. So it's going to be a win almost certainly. It's the kind of thing that programmers and compilers both try to do.